The two objectives for conservation of energy are the following. We're going to identify situations and solve problems when mechanical energy is conserved. And we're going to recognize different forms of the conserved energy. What does it mean to be conserved? If energy is conserved, what does that actually mean?
Saved.
What is it, Luke? The same? Is that what you said?
No, saved.
Oh, saved. Yeah, saved up. Sure, that's a good way to do it. If you conserve it, you save it, or you store it up, it's not being used up. So the idea is that the energies in these problems are not being used up. And that's one of our laws, conservation of energy, which states that for an isolated system, energy can neither be created nor destroyed. It can only be transferred. So you might think, all right, well, you know what? The power goes out. We ready, guys? The power goes out, and you start to turn a generator with a hand crank. You're creating energy. You're not really. You're transferring mechanical energy into electrical energy. So you're never creating nor destroying energy. That's the idea of conservation of energy. Okay, you're never creating nor destroying. Take a look at that in the second slide here. And I'll talk about these symbols. Okay, don't worry. They're very simple when I tell you what they mean. So first, the sum of the potential and kinetic energy in a system at any point in time is constant or conserved from beginning to end when friction is neglected. When friction is neglected. Okay? So what this means is the following. MEI equals MEF. Mechanical energy. Mechanical energy. And mechanical energy is defined as the sum, and I'm going to tell you that's what this means. This means the sum of the potential energies and the kinetic energies in the beginning of the problem. And that is equal to the sum of the potential at the end and the kinetic at the end. So if an object is currently not moving and it's sitting on this cliff right here, what kind of energy does it have? Potential. It's not moving, so does it have kinetic? No. So in the beginning, you would only use potential energy for MEI. It would only involve potential energy. But now let's say it jumps off the cliff. Halfway down to the ground, it's now moving, and it still has some height. So at the end here, we would use both potential and kinetic energy to figure out some values in the middle of the problem. When it hits the ground, does it have any height anymore? No. So it would have no longer any potential energy. It would all be kinetic energy, or the instant before it hits the ground, we'd say, because it's still moving, right? Remember that instantaneous velocity, impact velocity? So if we look at that, it would only be kinetic. So the idea here is that we need to look at the beginning and the end of a problem and isolate and write down the possible energies at the beginning and the end. Based on those values, we can solve for some missing numbers. Okay? Now, the second part of this says when friction is involved, we lose energy. We lose energy to friction. And that's what, and this your book doesn't do. I put this up here on my own. I like to call it Q loss. Q means energy. Remember Q equals MC delta T from chemistry? Q equals MC delta T. It was the thermal energy needed to change the temperature of a substance. Q represents energy. So I'm writing Q loss. I put absolute value around it. Because if you lose energy, at the end of the problem, you're going to have less energy than the beginning. So you're always going to be adding on this Q value, whatever it is. You're always going to be adding on a positive value. And think about it logically. All right, here we go. I start and I'm running with a certain amount of energy. What causes me to stop again? If I were to slide, what would cause me to stop? Friction. That's what Q loss would be. So in the beginning of the problem, I'm running and I've got a certain speed, right? I've got a certain speed, so I've got kinetic energy. But at the end of the problem, once I've slid and I come to rest, am I moving anymore? So it seems like I have no energy. So this balance wouldn't make sense. How can I have kinetic energy in the beginning, but potential's not even involved here because we're not at any heights? How could I have kinetic in the beginning and then no energy at the end and say that these two things are equal to each other? Well, that comes into play where Q loss is on the right-hand side. So if I have 20 joules of energy when I'm running and I slide and I come to rest, now I have no kinetic or potential energy. Where's all the energy go to? Q loss must be 20 joules for this to be balanced. So the energy that you start with in a problem must equal the energy at the end. But again, because you lose energy to friction, we need to take into account that value. Okay, and we'll do a bunch of examples that involve some sort of frictional loss. We already did one. Remember in class the other day where we looked at the work done and we set that equal to the kinetic energy using the work kinetic energy theorem, where the person was running with new socks and they slid on the wood floor and we found the distance that they traveled. What we were doing in essence is we were setting the kinetic energy before, the kinetic energy after, and Q loss. This was the friction force. And we were looking at these three components, KEI, KEF, and Q loss. Let's take a look at some examples. Okay, first, conceptual example is a pendulum swinging. When a pendulum swings, here's the motion. Just take a look at my arm. Here's a pendulum. That's all it's doing. Let's make believe that the pendulum is a string connected to a mass. The mass at the end we call the bob. Okay, the bob. So the bob is swinging back and forth. That's my fist. When I do this and I pause, like here, when I pause right here, the object stops, right, instantaneously in order to come back down, and then it stops. And then it comes back down. When it stops, does it have any kinetic energy if it stopped? So what's all the energy at this point?
Potential.
Potential, because it's got some height from the bottom. Now it falls back down to the bottom. It's at the bottom, so there's no longer any kinetic energy. But it's moving with the highest speed possible, at Vmax. Right? It starts to pick up speed, it picks up speed, it picks up speed. It gets to a maximum speed at the bottom of the path, and then it starts to slow down, slow down, slow down, and it stops. It gets faster, it gets faster, it gets faster, it slows down again. So at the bottom of the path, it's all speed and no height. So what kind of energy is at the bottom? All kinetic. So with a bob, if you wanted to draw an example on here, at the top, we'll consider this the ground level. At the top, all the energy is potential. At the bottom of the path, all the energy is kinetic. How about in between there somewhere? Yeah, both. And think about it logically. Ready? Here's my arm again. I go up to the top. I release it. And I stop right here. It still has some height, and it's now moving, right? So technically it's got motion, so there's kinetic energy. It still has some height above the ground, so there's also potential energy. So anything in between this, anything whatsoever, so something like this here, okay, that has both potential and kinetic energy. Because it's moving on its path on the way down, but it still has some height above the ground. Okay, it still has some height above the ground. So the simplest example of conservation of energy is a pendulum. Where have you seen this? There's a very good example. There's a very good example that you see on people's desks. Usually physics teachers on their desk.
The Chinese.
Yeah, what is it called, you know? Yeah, Newton's cradle, exactly. The thing where you drop the bob, it's connected to two cords, it hits, and then it picks up over here. Okay? That's also conservation of momentum. The idea that the momentum of this ball is transferred through the four different bobs into the outer bob, moving it. When you pick up two, though, what happens when you let go? Two go. Because again, conservation of energy and momentum. That's one of our best examples. Very little friction there. But over time, what's going to happen? Q loss. That's Q loss. Okay? Over time, you lose energy. That's what Q loss comes into play. Another example is an egg falling to the ground without air resistance or any object. At the top is all potential. When it's moving right here, it's part potential and part kinetic. At the bottom, it's all kinetic. Okay? We'll pick up from this next class. You're welcome to look ahead at the notes if you'd like to. So let's continue with the idea of conservation of energy. So the pendulum example, it started at a given height, and it would fall until it reached the bottom. When it reached the bottom of its path, it had no longer any height. So there was no longer any potential energy. And it just picked up speed, so it had kinetic energy. Analogous or a similar example to that is an object falling. When you drop an object, initially it's not moving. So it's all potential energy at the top when I drop it. As soon as I let go, it starts to move. So as soon as you let go, it picks up some kinetic energy. And it's also falling, so it loses potential energy. That's what this table is referring to right here. So let's take a quick look. The object is at a height of 1 meter initially, or 1 meter, I guess, initially, with no speed. So it's dropped. So all the energy is potential energy. There's no kinetic energy. So the total mechanical energy is just 0.74, which is the same as the potential. But as soon as it's dropped, after a tenth of a second, it has fallen 0.05 meters. And what we've noticed is that the speed has increased from 0 meters per second to approximately 1 meter per second. So that means that our potential energy is decreasing. Our potential energy goes from 0.74 to 0.70. So we lose around 0.04 joules of energy. Well, where does it go? It goes to kinetic energy right here. Okay, so in this problem here, we want to think about when an object falls, it's not only losing its potential energy, but it's gaining kinetic energy until it reaches the bottom. Now in this example, I didn't even go to the bottom here. I just kept showing how it decreased further and further. But what happens when it's about to hit the ground? What's the height? When it's literally right about to hit the ground, what's the height? there's no height really. So all the energy is no longer potential but kinetic. So if you wanted to draw a diagram, at the top of a free fall, it's all potential. Right before it hits the ground, it's all kinetic. Halfway there, it's half of half, or half of each. And then anywhere else, it's just part kinetic and part potential. Okay, so if you were to draw a diagram, and you wanted to draw it on the side, okay, here's what I would draw. An object falling, and just draw along the way at different increments until it hits the ground. At the bottom, it's all kinetic. At the top, it's all potential. Okay, here it's half kinetic and half potential, assuming the height is halfway. Here it's mainly potential but some kinetic. Here it's very little potential and mainly kinetic. So it's like potential mainly, potential mainly, potential mainly until it gets to about half of each. Then more kinetic, even more kinetic until it's all kinetic. So there's a constant transfer of energy going on here. You're not creating energy. You're not destroying energy. Neither of those things occur, but there's a transfer of energy occurring. Okay, transfer of energy. Any questions on this?
If this is without air resistance,
Without air resistance, absolutely.
then how does it max out kinetic energy? Because then wouldn't it not have any terminal velocity and just keep accelerating?
Well, the ground. That's what I meant.
Oh, when it's the ground.
Yeah. Something's going to stop at the instant before it hits the ground. So that's the max velocity you would get in a problem like this. If it was dropped from an infinitesimally large height, then yeah, it would continue to go without air resistance.
And but even without, like, it doesn't matter what point it hits the ground at. You assume that kinetic energy is all the potential has been converted into kinetic.
When it hits the ground. Because remember, potential energy is a relative term.
Oh.
It's relative to ground level. So if the ground level changes, the max potential energy changed, thus causing the max KE to change also. Yeah. All right, let's take a look at the first example, the next slide. So we did not do this one, correct? No. Okay. Starting from rest, the child slides down a frictionless ramp on a skateboard. If the height of the ramp is 4 meters, then determine the speed of the child at the bottom of the ramp. Now, this is a little bit confusing at first because people want to draw the ramp of 4 meters, and that's not what's happening here. So start by just drawing a little ramp. Put a little, child at the top up here, and then the child ends up down here at the end. Where's the 4 meters in this problem? Where's the 4 meters, Julian?
On the leftmost.
Yeah, on the leftmost part. Very good. It's not the length of the ramp, it's the height of the ramp. The length of the ramp is not known. Nobody cares about it actually in this problem. Okay, it does not matter. We're not given theta, we're not given an angle, we're not given this side. We can't use Pythagorean theorem to find the length of the ramp. It does not matter. Okay? Now, continuing though. It does matter where the bottom of the ramp occurs relative to the top, and that's 4 meters below. So we want to find the speed of the child at the bottom of the ramp. We need to, and this is a very simple example. So we're going to start with our basic conservation of energy. We'll say the mechanical energy initially equals the mechanical energy at the end. That was our conservation of energy theorem. Now, the second line of the conservation of energy theorem was, remember, the sum of the potential energy and kinetic energies. And that equals the sum of the potential energy and the kinetic energies. Here's what I'd like you to do. Identify what kind of energy this object has in the beginning, and then identify what kind of energy this object has at the end. Okay, write it down next to the object on your image. So list the type of energy it has here, and the type of energy it has here. That's all I want you to do. What type of energy does it have at the top of the ramp? At the top of the ramp, Lisa.
Potential?
Only potential. Why is there not kinetic, Lisa?
Because it's at the top.
No.
It's not moving.
Because
Starting
it,
from rest.
Yeah. Up here, take a look. Starting from rest. So you could be at the top of the path and have some initial velocity. Remember the objects that were launched off cliffs?
yeah.
Those had a VI. So those would have kinetic energy and potential energy, both. But in this problem, the child is sitting at the top from rest. And then he just starts to slide down. So we say that in the top, there's only potential energy. At the bottom, what kind of energy is there for this problem? Why kinetic, Luke?
Never mind, I withdraw.
No, don't withdraw, you're right. Why kinetic, Luke? Why kinetic? What is kinetic energy? Come on, don't hide. You know this. What kind of energy is kinetic? Kinetic means what? Kinetic means? Motion, yes, good. Stored is potential, yeah. So Luke, I'll come back to you now. Why is it kinetic? Yeah, exactly. The child is moving at the bottom. So there's kinetic energy. Now, Luke, you're going to ask another question here. Why is there no potential energy at the bottom? Luke, you know this. Why is there no potential energy at the bottom when he's on the ground, when the person...
Because the object's moving, it's not at rest.
Okay, I mean,
There's actual energy happening.
okay. But remember, what did potential energy? What was the formula? Remember the formula? It was mgy. Mgy.
Yeah.
What does y represent, Luke? Yeah, so where is it along the y-axis right now?
Oh, it's at zero.
Yeah, exactly. It's at zero height. So there can't be potential energy when you're at ground level. Okay, so we're at ground level, there's no height, so there's no potential energy at the bottom there. Okay? Now, based on that information, focus. Based on information, we can list what we have in the beginning. Again, the beginning is only potential energy. So for MEI, please just write potential energy initially. There's no kinetic energy initially, so we don't have to write it down. If you wanted to, you can, but you would cross it off and put 0 there. The energy at the end is all kinetic, so that's kinetic energy at the end. So for this kind of a problem, there is no need to list PEF, because there is no potential energy final. There's no need to list KEI, because there is no kinetic energy initially. So you don't even have to write them down. Okay, in our equation, I use the sigma sign. Remember the sum of all those energies. But just list what you have at each location.
So is this like mechanical energy thing combining where all the little stuff we're doing and putting into one giant thing?
What do you mean?
Like how we would do, just like solve for potential energy like in a single problem, but now we're solving for both at the same time.
Yeah, so we're combining the stuff we've done with energy so far and looking at it as a whole picture of a system. Instead of just potential or just kinetic or just looking at like velocity, we're putting all those ideas together using conservation. So we're going to do examples like objects are launched at different angles, and we're going to have to think about potential and kinetic energy now. So we're going to talk about how that changes as a function of time. Okay, but the idea of conservation is what's important here. You can't lose energy, it just transfers, just changes. So in this problem, I want you to go ahead and plug in your variables for your formulas you know. You have these formulas in your notes. So if you need to go back and look or look at your cumulative formula sheet, please do it. But you have a formula for potential energy, and you have a formula for kinetic energy, both. So you need to look at what those are and list them. Replace PE and replace KE with what you know.
Oh,
What's the formula for potential energy? Who's got the formula for potential energy? Dylan, what do you got?
MGY.
MGY. So for this one, I'm going to put MGYI to indicate that it's the initial height.
Can we use H?
If you would like to use H, it's okay, but I traditionally like to use Y because Y represents the displacement of the object, and that's what we're looking at. If you want to use H for height, if that makes you feel better, that works. It does, but just make sure you're... Huh? The textbook probably does use H, but it's not the highest level textbook, so I would rather use Y just because of the fact that we're looking at displacement here. Okay? What is the formula for kinetic energy, Teresa? 1/2 mv squared. Now call it VF squared. Okay? So for this problem, we've got MGYI equals 1/2 mvf squared. mvf squared. What do you notice? 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 They both have m. So what should we do with the m, Gio?
Cancel.
Yeah, let's cancel them both out. Okay, they've both got m's involved. So when we drop those m's off, we're left with GYI equals 1/2 VF squared. Again, drop the m's off, we're left with GYI equals 1/2 VF squared. And yeah, good, because what are we solving for, Gio? Yeah, we're solving for the speed at the bottom of the ramp, which is our VF, our velocity at the end here. Okay? Now, if we move over the 1/2 by multiplying by 2, this is what we get. And then we take the square root. Now, it's really kind of cool to notice. This is the same answer you would get if you used your kinematic equations of motion. Remember, VF squared equals VI squared plus 2AY or 2AX. We use those in chapter 3. If you use that formula, you get the exact same answer. So for a problem like this, it really doesn't matter which way to solve it. But for the problems we're going to do in a moment, it's a lot easier to use these new energy methods than it may be to use old school projectile motion methods. Okay? Old school, meaning we did it, in the past. Back in the day. So again, if you had used this instead, just so you know. Okay, if you had used this equation instead, you get the same answer. VI is 0. This would drop off. And take a look. 2AY. 2 times A times Y. That's this. 2 times G times Y. G is A. And you take the square root to get VF by itself. It's the exact same answer. Okay, exact same answer. Either way you do it, you have the same answer. But again, for the sake of today, we're doing energy method, so you don't need this. Okay, but just to prove to you that you get the same result. What do you get as a numerical value for VF when you plug in? What do you get as a numerical value here? You should all check this, please. Have your calculator out. Let's go. 8 point. You do indeed. Good. Please, everybody, check these either way. Whether you got it or not yet, check them. I don't know who that was, but just heard that word come out. I don't want to hear. So 8.9 meters per second is our final velocity, or the speed of the object at the bottom of the ramp. Okay, at the bottom of the ramp. And this is rounding, obviously. I think it was 8.86, 85, something. Okay. Please remember for these problems that you don't need to make G negative. Okay, it's 9.81. The negative only came into account when we were looking at projectile motion because it was negative acceleration downward. Okay, but our formula for kinetic energy and potential energy involves mgy, where G is the positive. Remember that the negative quantity in the front here kind of is encapsulated because it's moving down. Okay, we left that as a positive 4 there. All right. Let's take a look at the next one. So example 2. A pendulum bob is released from some initial height such that the speed of the bob at the bottom of the path is 3 meters per second. A, determine the initial height of the bob. B, at what height will the potential and kinetic energy be the same? So let's start with part A first. Now again, it may be useful to draw a diagram. So start with the normal pendulum. Okay, how did we draw the pendulum last time? Just what? We did. In the top right. I drew it. You had to do it. We drew it like this. I'll reiterate.
9 and a square.
They did that with the last class.
Yeah? Okay. Alright. So, remember the example though I talked about with a pendulum moving? This is how you would represent a pendulum in motion. Now, when the pendulum is raised to the top point of its path, okay, it's raised up and then it's released. Pendulum is released from some initial height. When it's at the top of its path, okay, when it's at the top of its path, what kind of energy? What type? Potential. Why potential, Ev? Because it's not moving? Okay, it's not moving tells us there's no kinetic, but it doesn't tell us there's potential. Because I need something else to tell me there's potential. What is involved with potential energy, Mike?
Well, it's at the top, it's like height, it's like the highest moving.
So it's got some height, we'd say. It has some height. That's the key. The fact that it's not moving just tells us that there's no kinetic, which is a part that we need to write for sure. We need to realize that there is no kinetic in the beginning. But the key is that the height of the potential of the pendulum is what causes the potential energy. Okay, the height of the pendulum. We are told that we need to figure out what that height is, right? Look at part A. What is the initial height? So we're trying to figure out how high off the ground this pendulum is. Now, at the bottom of the path, we could say that the height is 0, right? Again, the example we did before was talking about the desk being the bottom of the path. So a pendulum that's swinging through motion is at some max height here, and at the bottom there is no height. Okay, there's no height. What's at the bottom? What kind of energy is at the bottom? Why is there kinetic, Camila? Why is there kinetic at the bottom? You're correct, but why? Okay, so there has to be some conservation, but what's the real reason though? Yeah, it's picking up speed. The minute an object is moving, it has kinetic energy. Now, you're right to say that because the potential energy is decreasing, it has to go somewhere, the energy goes into kinetics. So you're right by saying that also. But the key we want to think about is that there is kinetic energy down here because there's some velocity of the pendulum at that location. It's given. It's 3 meters per second. So here's what I want you to think about. A problem like this is your initial up here. This is your final down here. Clearly the pendulum swings back and forth, right? But we are piecewise, we're looking at like a piece of this function. We're partitioning. We're saying, you know what, we'll call this the beginning right here. It's released. And we'll call this the end right here. Sure, it will continue to move on. Okay? But we're going to look at initial as the top and final as the bottom. So initially, we have again, we start with MEI and MEF. We then go on. List the energies in the equations. So initially we said that the object was starting at some given height. So that's got to be the potential. So instead of MEI, we'll write PEI to start. There is potential energy at the beginning of this problem. Is there any kinetic at the beginning? No, because it's not moving. It's being dropped from rest. So we don't have to write kinetic at the beginning at all. We'll just ignore it for now. That's what I was saying before. Now at the end, what kind of energy does the object have again? Kinetic. So we'll say KEF, kinetic energy at the end of the problem. But a minute ago we said there is no potential energy at the end of the problem because it's at ground level again. So we don't even need to list potential energy at the end. So that's what I'm trying to get at. You don't need to write every single time. PEI plus KEI equals PEF plus KEF. It's kind of pointless. It doesn't make sense. It's more time. So just list the energies you do have at those times. So in the beginning we have potential, PEI. At the end we have kinetic, KEF. And that's all we have to list. Now we can plug in numbers. Do you notice something about this problem? Do you notice something about this problem with respect to the previous problem? It's the same thing. It's the exact same problem. You have the exact same equations. Except now we're trying to find YI, the initial height. In the last problem we were finding VF, the final velocity. But now we have VF. So it's the exact same problem, these two. They're not all going to be the same. They're not. But I want to show you that two completely different sounding scenarios can have the exact same algebraic scenarios. Okay? So here we have MGYI equals 1/2 MVF squared. The exact same equation. What cancels again? Yeah, the mass has got to cancel. We're not giving it. It cancels on both sides. And this time we're solving for YI. We're trying to find the initial height of the pendulum before it has been released. So Mike, what do I want to solve for YI? Not numbers, but variables.
YI equals 1/2 VF squared over G.
Very good. Okay? So just divide by G, please, on both sides. You can go ahead and plug that in your calculator to see what number you get. Now, please keep in mind that you could also write this as VF squared over 2G. You can move the 1/2. You can put the 1 up top and put the 2 on the bottom. Everybody see what I'm saying? See this 1/2 in the front here? the 1 is really part of the numerator, the 2 is really part of the denominator. Because technically speaking, if I multiply by 1/2, it's the same thing as dividing by 2. So you could write this, you don't have to, but you could write this as the following.
VF squared over 2G.
Yes. Okay, it's the same thing. You'll get the exact same answer, try it. Okay, so keep that in mind. Whenever you have a fraction within a fraction, you can associate the numerator and denominator of the number part in the top and the bottom. Okay? What do you end up getting for velocity, Joyce? Or height, sorry? 0.46. And my units are? Height? Good. Okay, the height is given in meters.
Why isn't it 2y? Get rid of the half.
Because remember, we're not getting rid of the half. Last problem we were solving for VF, right? So we got rid of the half by multiplying by 2. But now we're solving for YI. So we leave this alone and just divide by G. Okay? So here there was GYI, so dividing by G, we get 1/2 VF squared all over G.
Yeah, but then you have VF squared equals 2g.
I then wrote it as VF squared over 2G. If I asked you, you have a dollar, what's half of a dollar?
50.
If you take a dollar and divide it by 2, what do you get? So if I put this 1/2 here, or if I divide by 2, it's the exact same thing. So I was just showing it. Okay? So we get a height of 0.46 meters. That's the initial height of this pendulum. Now, we want to know as a follow-up question, when will the kinetic and potential energies be the same? When will the kinetic and potential energies be the same? So what can we do? What can we think about? Philip?
This is a concept question.
Can you just divide 0.46 by 2 and that's your answer?
Why?
Because they're equal at halfway.
Yeah, remember the other day we were talking about this? If an object is falling to the ground and it has a height of 10 meters, okay, say the height is 10 meters, it's got a certain amount of energy. Once it's fallen 5 meters, it's got how much of its energy left in potential? Half of it. Where did it all go? To kinetic. So half of it is potential and half of it is kinetic when you're at half height, right? So that's all you need to do for this. Part B is just 0.23. Again, an object falls halfway down, that means it loses half of its potential energy. Where does the other half of it go? It goes into kinetic. So if I started, remember, let's say I started with a total energy of 100 joules. As soon as it falls halfway down, there's 50 joules potential and 50 joules kinetic. So say I started with that much potential, then it splits into kinetic and potential. Okay? Half is kinetic, half is potential on the halfway point. Then when it hits the ground, what is it all? Zero potential. So what is it all? Kinetic. It's all kinetic at the bottom. At the bottom, there's still 100 joules. Remember conservation, but now it's all kinetic energy at the bottom. So the answer to part B is just half of this number, or 0.23 meters. And again, half of the height of the object represents half of the potential energy. Let's move on to the next one. In the beginning of the problem, the person has a certain height. So the person must have what kind of energy to start this problem? Potential energy because he's at a height. At a height. Now, what other kind of energy exists in the beginning and why? Why?
Because he's jumping.
Yeah, he's jumping with a velocity of 4 meters per second. So he's also got kinetic energy. So in the beginning we've got potential and we've got kinetic. At the end, what kind of energy exists at the end?
Kinetic.
Why?
Because he has that height of 0.
Yeah, his height is 0, but he's the instant before he hits the water. So he's still moving. So initially we've got both potential and kinetic. At the end we've only got kinetic. Okay? Now, based on the information, just write your equations of conservation. Start with MEI equals MEF. The stuff that exists in the beginning, put for MEI. The stuff that exists at the end, put for MEF. James.
In theory, couldn't you just calculate how high x to the top of the hat and then treat that as GC and then calculate from there?
Sure.
If you follow?
But the problem right now, well, not the problem. You could do that. You would have to use VI sine theta to get the VIY, set VFY equal to 0, solve for the Y max, add that Y max, to 8. Use that as your PE total. It would just take more work to do that, but yes, you can. You would be combining kinematics with energy methods. Okay? So James is saying, why not find the max height using old school kinematics and then just use that as potential energy in the beginning, falling to the bottom. Chris?
What is that same thing?
PE plus KE,
Oh.
and then this is just KE at the end. So mechanical energy initially equals mechanical energy final. In the beginning we have potential energy and we have kinetic energy. At the end we only have kinetic energy. Please use subscripts, okay, because KE is not the same thing as KE. KEF and KEI are clearly different things. Please use subscripts. Continuing down, we've got MGYI plus 1/2 MVI squared equals 1/2 MVF squared. So what do you notice, folks? What cancels again? So these energy problems, it seems that the M's don't matter. And they will matter at one point. And when we get there, we'll see that. But for this example, the M's don't matter because they're always dropping off.
I was trying to think when ends would matter.
Can you think about it already? There is an example.
Yeah. I don't tell you that.
All right, then hold on.
Got it. I know what it is.
When would M's matter?
And why?
No, I got it.
Nope.
When you would be calculating the object before it hits the ground, where it's like
In the middle.
yeah, in the middle. Not in the middle, but before the middle. After the
Still,
middle.
mass would still cancel. Mass,
When there's both a potential and a kinetic in both.
it would
parts.
still have M's in all
When there's
four,
no
and they would all cancel.
That would be 3. There would be 2 and 1. And
Doesn't matter, guys. Remember, folks, hold on.
And it takes in everything that's in the
Yeah, let me pause and stop for a second. These two M's cancel with this M. It's not like 2 and 1, because you're factoring an M out, and then you're canceling it, really. Again, if it makes it more clear, factor an M out and write it like this.
wait, so if there's 2 M's on one side and 1 on the other, you can still cancel.
Absolutely, because they're in every term. Remember, the whole idea is that they're in every term. So look, here. This M that I just factored out front
No, that makes sense.
cancels with this M here. That's why I can do the previous line that way.
So if you have
But if you have 4, they all still cancel. When will the M's not cancel? What kind of energy have we looked at besides normal potential energy and kinetic? What is it? Elastic. What was the equation for elastic potential energy or spring energy?
1/2 x squared.
Kx squared. Is there an M in there? That's the problem, okay? If you have a problem with a spring, the masses aren't going to cancel. And we'll see that in a moment. Let's continue, though, because this example does have cancellations.
Can you use potential kinetic energy in the same problems as spring energy?
Sure, of course. An object is loaded into a spring. It is launched. It launches off to a certain height. Then it ends up on the ground. You have potential energy, you have kinetic energy, you have potential in the spring initially. Absolutely. Please.
Why do you keep writing mechanical energy?
Just to remind myself of conservation of energy.
So
This,
you don't actually use that.
this just tells me the energy before equals the energy after. That's what I'm starting at. And then I plug in what I have before, and I plug in what I have after. Okay?
How do you know when you're going to, because it's like a thing in physics, how do you know when you're going to use which equation, depending on...
Well, for these problems with energy methods, when you're solving by energy methods, you need to look at the scenario and see what's going on in each instance. So, in the beginning there was motion and height, so you use potential and kinetic. At the end there was only motion, so you use kinetic. But as far as like a midterm where you'd have this problem, you could choose to solve this by using kinematics and use the old school formulas or use energy. That's up to you to choose. I can't tell you which way to do it or not. Either way works.
Would you ever use like the work equation in here?
No, because we don't have a force applied over a distance. Remember, work is FD cosine theta. So we don't have force times distance in these problems,
As though
okay?
work was 1/2 mv squared minus 1/2 mvi.
That's the work kinetic energy theorem. That has to do with when there's a force applied and there's object moving and the object slows down because of some force being pushed. But you're giving nothing about a force here, you're giving nothing about friction or anything like that. So you're not going to really use that one in this, okay? All right, let's continue down. Continuing onward, we were trying to figure out the object's what?
The object's final velocity.
Final velocity before it hits the water. So VF. So what do you want to do?
Multiplied by 2.
Yeah, let's multiply by 2 to get rid of this 1/2 right here.
Then take the rest.
Because when, if
Take the
So
square
can the
root.
1/2 cancel?
Not because it's in every term, though.
Take the square root.
Hold on, I'll show you.
Wait,
Multiply, watch. Multiply by 2. Multiply by 2. You're distributing the 2, aren't you?
Yeah.
So it only cancels with one of them. That's why this VI becomes VI squared just by itself here. Okay, but the 2GI has to be noted in the front. Again, you're multiplying everything by 2 to get rid of that 1/2 there. Then take the square root at the end.
So it's square root 2GY plus VI.
Okay, now, please be careful here. A lot of you are going to be tempted to try and cancel the VI squared with the square root. You cannot do that. Remember, this is a sum. This is the sum of two numbers underneath a radical. You can't just cancel the radical with one of the squares. It doesn't work like that mathematically. In order to cancel a square under a radical, the whole entire thing needs to be squared. Again, just to make this point. If the whole thing, 2GYI plus VI, if this entire thing had been squared, then you could take the square and the square root and cancel them. You cannot cancel the square root and the square that currently shows up here.
you have to plug it in first.
So we have to plug in numbers and then take the square root. Yep. Okay, let's plug in numbers. What do you notice? Did that angle of 23 degrees even affect this problem?
No.
It does not affect the problem. And that's one of the great things about energy methods. The angle of launch doesn't affect it. So you're not going to end up using sines and cosines for this. Okay, so it makes it a little bit more reasonable for some students in this problem.
What if you're not given a velocity? You just solve it.
Well, then if you're not given VI, you can't solve this problem.
I know.
How could you? You would be missing a variable. Okay, let's plug in.
There's no connecting variable.
There's no linking variable to plug in now. What was the height? 8 meters?
Velocity is 4. Square.
What's first ratio?
It's 416.
It's actually the 116 meters per second.
Okay. So for this problem, let's go ahead and plug in. What do we get for a number?
13.2.
13.2? 13.2.
I taught you.
Others, please check. Others, please check.
Based on the trajectory of the sun and the moon.
Hey, let's do one more for today. Let's do one more for today. Now, you want to shoot a rubber band.
One more.
You want to shoot a rubber band that has a mass of 3 grams. Notice the mass is given now because already it's a rubber band. So we're going to have what kind of energy? Elastic spring energy here. So you have to be given a mass. Now, you want to shoot a rubber band across the schoolyard from an elevated window of 7 meters above the ground at a classmate who's 2 meters tall. So preferably hit Luke in the top of the head. You know that you can stretch the rubber band a distance of 10 centimeters if the rubber has a spring constant of 0.2 newtons per meter. With what speed will the rubber band hit your classmate in the back of the head? Okay? Please do not try this at home. It's my disclaimer at the bottom. Okay, so we have a lot of information here. We have a real lot of information. We're starting at some height at a window. So let's say that the object starts at this window. Okay, it's 7 meters above the ground. It's clearly a rubber band. I'm just drawing a box though. Okay, the rubber band is going to hit a person. It's going to hit the person in the top of the head. So the rubber band is going to hit them here. Are you enjoying making that noise? And the height of the person is 2 meters. Okay, so we have to think about the fact that we have initial potential energy and we have final potential energy. Okay? So it starts at some height, but it's not going to end up on the ground. It's going to end up hitting the person in the head. That's the end of the problem. We want to know the velocity when it hits the person in the head. Okay?
Why velocity?
Can you just consider, can you just subtract 5 and 2 and then get 5 and you can just say 5 is the
Yes.
ground level?
You could say that the person's head is ground level and that it travels a distance of 5 only. You could do that. I want to do it this way just to show that you could have potential energy at the beginning and at the end. But you absolutely can do that. You know that the initial velocity, I'm sorry, not initial velocity, you know that the initial stretch of the rubber band is 10 centimeters? Is 10 centimeters. So what is that in meters? 10 centimeters?
Point one.
No, down.
0.01.
Oh, one.
0.001.
Wait.
All right, good. 0.1 meters. You guys got to practice here. Come on. Centi is 100. 100 is 2 zeros. Move it 2 spots, please. Move it 2 spots. We will eventually square it, yes. Absolutely. The K value is given. What's the K value in this problem? How do you know that? Who can tell me? How is the identifying factor?
Newton per meter.
Yeah, the units. Okay, the units tell you that it's K for sure. And it also says spring constant. We know that the initial height of the object is 7 meters. Testing my patience. We know that the final height of the object is 2 meters. We are not told anything about initial velocity, so it technically starts from rest, and it does. You're pulling back on the rubber band. As soon as you let go, the energy begins to convert from there. So there is no initial velocity. Even though I know that as soon as you shoot it, it's going to be moving. But the problem is starting from this point. Ready? I pull back the rubber band. This is the beginning of the problem right now. Because I've got energy. Do you see that? I've got stored energy in the rubber band. So this is the beginning. So right now it's not moving. So there is no initial velocity in this problem. And that's the tricky part. Even though you want to say, yeah, it's moving. As soon as you release it, it starts to move. But when you pull back on the rubber band, it's not moving.
But the initial velocity is when you let go, right?
And that's what I'm trying to get at here. For these energy problems, the beginning of the problem begins as soon as there's energy. As soon as you pull back on that rubber band, don't you create energy, or don't you not create, transfer your arm energy or mechanical energy into the spring. So as soon as it's pulled back, the problem begins. So there is no initial velocity here, because we're looking at the point where the rubber band is now stretched. So we could say VI is 0, and we're looking for VF. And that's really all we've got.
No, the mass.
Okay, sure, thank you, absolutely. And 3 grams is?
0.003 kilograms.
Yes. Okay, remember it's in kilograms only. So we take 3 grams as our mass and convert it into kilograms. Now, at the beginning of the problem, the object has a certain height and it's being stretched. So we've got potential energy for height and potential energy in the spring to start. There's no velocity, so there's no kinetic energy in the beginning. So in the beginning, again, we've got potential energy and we've got potential energy in the spring. This is what I want you to be writing on your diagram so you know what you're doing. At the end, there still is some height in the problem. It hits the person's head, which is 2 meters above the ground. So there is some potential energy at the end. But it's also moving at the end, so there's kinetic energy at the end. With the object is no longer stretched. You stretched it in the beginning. Once you let it go, that stretch now contracts and the rubber band just kind of topples down to the ground or to the person's head. But it's not stretched. Once you let it go, that spring energy is what propels it forward. Okay? It propels it forward and it's not stretched at the end of the problem. So we have mechanical energy in the beginning equals mechanical energy at the end. In the beginning, we've got potential energy plus potential energy in the spring. And that is equal to the energy at the end of the problem, which is potential energy at the end plus kinetic energy at the end. Please note that if it's a spring involved, you must or you should designate with an S here so you know that these are 2 different things. Please, again, put an S right here so you know that these are 2 different quantities or 2 different entities. What are we trying to find again? So we're going to be solving for something that is in here. Again, look at the equation. We're going to be solving for something that's in your KEF because we're trying to find the final velocity. Let's plug in our equations.
Wait, so if we know like that something we're solving for isn't a specific thing, we just
Solve for that first? Sure. Absolutely. You could.
We just like
The masses do not cancel.
Oh, yeah, what?
Please notice that there's no mass in the kx squared formula, so you can't just drop off all the m's. Remember, something only cancels when it's in every term. Every term, every term, every term. It's not here. You can technically factor an m out of this, but you cannot factor an m out of here. So you can't cancel mass. Okay, if that's confusing to you, you need to come see me and I'll show you. But I'm not going to spend time going over that. But please remember that if mass is not in every term, you cannot cancel it. We are trying to find VF squared, so we should move over the mgyf by subtracting it. So let's move this over by subtracting it. mgyi plus 1/2 kx squared minus mgyf equals 1/2 mvf squared. It's just algebra from this point on, right? We're just moving stuff. So take this entire expression and we move it over. How do I get rid of the 1/2?
Multiply by 2.
Multiply by 2, and then I want to divide by the mass. So multiply by 2. And then divide by the mass. Okay? So again, multiply by 2 to get rid of this 1/2. We have activities, so no rush. Multiply by 2 by putting a 2. Multiplying this entire expression by 2. That's this. Then divide by the mass by putting the mass there. We have a squared here. What do I do at the last step to get rid of the squared? Square root it. The whole thing is under the square root. So I recommend when you're doing this on your calculator that you do the whole numerator. Come up with an answer. Hit divide by the mass. Come up with an answer. Then press second square root, second answer to do the square root of the result. Okay, to do the square root of the result for this one.
That's already what I did.
Yeah? Okay, the number you'll get, and you can check this on your own, should be 9.94. That's what I got for VF if I rounded or if I didn't round as much. Okay, the speed. Tristan, hold on. Come on, I'm still talking. I understand, but you can wait another minute. The final answer for VF is going to be 9.94, and it's really plus or minus because we're taking the square root. But the problem says, with what speed will it hit the person? And remember, speed is always positive. Okay, velocity could be positive or negative, but a person's speed is always positive. So your answer will be 9.94 meters per second when you plug into this. Okay. There is one more example. We're going to definitely go over that example in class, but I want you to still do the homework in this section. Okay, you can still do it without the last example. You can definitely still do it. The last example involves losing energy to friction also. So we have to use that Q loss that we talked about. Okay? So what I want you to do tonight is do every problem, unless it involves friction and there's some energy loss in the problem, which I think might be only one of them. Okay, so please do it tonight. Have it ready for tomorrow.
So don't do
Okay.
the energy, friction.
Again, if a problem involves friction, you don't have to go ahead and do that. I do have you guys tomorrow, right? Day 3?
Yes.
Okay. We have a double? Okay, so we're gonna meet in the lab tomorrow for the whole double. We're gonna meet in the lab tomorrow, if I recall correctly, yes. Okay? I'll put it in the announcements though so you can see that as well. Mass of 4 grams is slid across the rough surface of a lab table. That surface has a coefficient of kinetic friction of 0.5. If it starts moving due to a spring with stiffness 15 newtons per meter that's compressed 12 centimeters and then released, how far will it have traveled when it's moving with a speed of 4 meters per second? So a problem like this, we have to realize right away that we're on a lab table and we're not moving height, so there's no potential energy involved in this problem at all. But there is spring energy, elastic potential, there is kinetic energy involved, and we're losing energy due to friction. That's that Q loss we were talking about. So a problem like this, we have to think about the fact that here's our lab table. Here's the wall, or whatever the spring is. The spring is compressed. Here's the object. It's then released, and the object begins to move and ends up over here. And we want to find how far it has moved, the distance d, okay, with certain parameters involved. So let's take a look at the kind of energies. So when the spring is compressed completely, all we have is spring energy in the beginning. So in the beginning here, in this part, we have potential energy in the spring. Now at the end, it's moving, so we have kinetic energy at the end. But remember that there's the coefficient of kinetic friction in this problem, so we're using friction. So we also, at the end, have to consider the fact that we've lost some energy. So some of that spring energy went into kinetic energy, and some of it went into energy loss due to friction. So we need to remember to add on the absolute value of our energy loss here. Well, if we think about this, we really have to say the potential energy is a certain value. Not all of it is going into kinetic. So say this were like a value of 10 joules, maybe 6 joules of it goes into kinetic energy, and the other 4 joules goes into heat loss or friction loss. So based on this information, let's list what we can. We know that MEI equals MEF. But remember that now this system involves some sort of energy loss. So we could say that we have 1/2 kx squared equals 1/2 mvf squared plus some Q loss, some energy loss in this problem. Again, the spring energy is the 1/2 kx squared in the beginning. The kinetic energy at the end is the 1/2 mvf squared. Q loss is our energy loss due to friction. So we have to remember what is causing this loss due to friction. That's the key here. And the thing to remember is that it's the force of friction. So it's the force of friction times the distance it covers times the cosine of theta. Okay, and we have to remember that. That comes from our work equation. Remember the work done on the object due to friction. Again, this is the work done on the object due to friction. That's how much energy is lost. So for a problem like this, we are trying to find this D right here. That's what we're looking for in the end. But remember that FF is really mu Fn. That's what FF is equal to. Okay, I'll write it on the side up here is mu Fn. So the coefficient of friction times the normal force. But because this object is only moving horizontally, the normal force is the same thing as the weight. They're equal and opposite each other, which we've seen several times now. So it's just mu Fg. But remember that weight, Fg, is really mass times gravity. So we're going to take this quantity and replace FF with it. So this equation becomes 1/2 kx squared equals 1/2 mvf squared plus absolute value of, now replacing FF with mu mg times d times cosine theta. The important part to think about in this problem is the fact that cosine theta really doesn't matter because it's actually 180, but we're going to take the absolute value in the end. So the cosine of theta has no significance on this problem because, again, friction acts opposing motion. So since motion is to the right and friction is pulling back to the left, our angle theta is going to be 180, but we're taking the absolute value. So it doesn't really affect the problem at all. Now, we want to solve for D. Okay, we want to solve for D in this problem. So let's move over the 1/2 mvf squared, giving 1/2 kx squared minus 1/2 mvf squared. And that is equal to mu mg d. Okay, again, I can put the cosine of 180 there, which is -1, but we just take the absolute value in the end anyhow, so it doesn't make a difference. Remember, the reason we're using this absolute value around Q loss is to remember that in the beginning of the problem we had a lot of energy, and most of it turned into kinetic energy, but some of it we lost due to friction. So we have to consider the fact that this has to be some positive quantity of energy. Okay, it's got to be some positive amount. So we put the absolute value around it to indicate that point. So now we're trying to find our value of D in the second side of this equation. So let's factor out a D to start this. If we factor out the D, we're going to end up with 1/2 kx squared minus 1/2 mvf squared, and that equals D times the quantity mu mg. Okay, and that's in absolute value there. So let's go ahead and divide by mu mg. Which pretty much erases it from this side of the equation. So the distance this object will travel in the end is really the differences in the energies between the spring and the kinetic energy, really, but then we're dividing this by the quantity absolute value of mu mg. Now remember that mu is given in the problem as 0.5, the kinetic coefficient of friction. M is given as a mass of 0.004 kilograms. It was given as 4 grams when we convert it. G is always given as 9.81 meters per second squared. K was given in the problem as 15 newtons per meter. The distance stretched was 12 centimeters or 0.12 meters. The final velocity in the problem was 4 meters per second. We can plug that in there, and we know the mass again. Notice that the mass does not cancel here, because we have mass only in 2 locations, not this third. It would have to be in every term in order to cancel out the m's in this problem. If we plug in all of our known values here, we end up getting a total distance of 3.87 meters. Remember that distance is measured to be positive, okay, so we're not looking at the displacement of the object, but the distance traveled. Your homework from this section is 3 problems from page 185 and 186.